Hello, this is Professor Kuehn. Welcome back to my lectures on space, time, and motion, where we are talking about Einstein's theory of relativity. In this, which is probably my last lecture on relativity, I just want to highlight some of the similarities and differences between Newtonian mechanics on the one hand and relativistic or Einsteinian mechanics on the other hand. So I'm going to do this by means of a table. So once again, this is a comparison of Newtonian, or we might say classical mechanics, and Einsteinian, or we might say relativistic mechanics. Okay, comparison of these two different approaches to mechanics. Okay, so let's start out by talking about Newton's second law. So what was Newton's second law? Well, I'm going to make a table here. So according to Newton, it's that when a force is exerted on an object, it causes its momentum to change at a certain rate. So F equals dp dt. Can we use the same formula in relativistic or Einsteinian mechanics? And the answer is yes. We can use the exact same formula. We don't have to change that formula at all, which is reassuring. What about the concept of momentum? Or the definition of momentum. Remember, according to Newton, momentum, or what he called quantity of motion, but we now call momentum, it's the product of the mass of an object in motion times the velocity of that object that's in motion. Can we use this in relativistic mechanics? And the answer is yes. We can use the same formula once again. So that's still true. It still works. But there's an important caveat, and that has to do with our understanding of mass. In Newtonian mechanics, the mass of an object we take to be the rest mass. So this m sub 0 is what I will call the rest mass. That is the mass of the object if it's sitting on a scale in front of you. And in Newtonian mechanics, the mass of an object does not change when it's in motion. The mass remains the same. So the mass that appears in this formula is just the rest mass. Well, in Einsteinian mechanics, one can consider the mass to itself be velocity dependent. That is, the mass is gamma. That's the gamma factor that had appeared in our relativistic time dilation and length contraction formulas. So gamma times the rest mass. So in a sense, the mass behaves in a way that is dependent upon velocity. So this is the mass that one puts into here. So the formula technically is gamma times m naught times the velocity, or once again, m naught would be the rest mass. Okay? What about the concept of energy? And again, I'm not really justifying these at this point. I'm simply listing the similarities and differences between Newtonian and Einsteinian mechanics. Well, in Newtonian mechanics, the idea is that the total energy of an object can be broken up into the kinetic part of its energy plus the potential part of its energy. So this is the energy of motion, or the energy associated with motion. This is the kinetic energy. And this would be the energy associated with its configuration, or configurational energy. Configuration energy, or we would say potential energy. It has to do with the fact that the object is at rest, but that the object at rest might adopt various configurations. So for example, you might have two masses attached to a spring, and the amount by which the spring is stretched is an indication of the resting configuration of that object. And one must do work to stretch the spring. That shows up as spring potential energy, and that fits into this U right here. That would be the potential energy of that two mass and spring system. But I just want to highlight that we're really dividing the energy into a kinetic or a motion part and a rest part. Okay? And by the way, the kinetic energy is just 1/2 the mass of the object, and maybe I'll just highlight that this is the rest mass times the velocity squared. So that is the kinetic energy that appears in the energy formula in classical mechanics. What about in relativistic mechanics? Well, the energy of an object is mc squared, where once again this is the relativistic mass. So we might write this as gamma times m naught times c squared. Okay, So that would be the total energy of an object. That's the combination of its rest energy, you might say, and its kinetic energy. It all is subsumed into this generalized energy formula. Let me say a couple of things about this. And you may or may not be familiar with some of the mathematical concepts I'm going to talk about in a moment, but just bear with me if you're not. Okay? So what is gamma? Once again, remember gamma is 1 over 1 minus v squared over c squared square root. Right? So I'm going to go ahead and explicitly plug that in for gamma. And now what I want to do is I want to highlight that this right here can be expressed as a Taylor expansion or a series expansion. If you're uncomfortable with this, that's okay. Just bear with me like I said. A function like this can be written as an infinite series in terms of this quantity in the denominator. So if you want to look in your calculus book, you can look up what that series expansion is. Otherwise, you can just trust me here. That quantity in parentheses can be written as an infinite series 1 plus 1/2 of this quantity down here, v over c squared, minus 3/8 that quantity v over c to the 4th power, plus, and so on and so forth. There are an infinite number of terms, but when the velocity is small compared to the speed of light, you get a small number squared, a small number to the 4th power, a small number to the 6th power, and so on. So these terms get less and less important, smaller and smaller terms. So let me finish writing down this expression, m naught c squared. And if you were to multiply these terms out, the first term would be m naught c squared times 1, so you have m naught c squared. What about the second term? Well, you have a c squared here and a c squared in the denominator, so those cancel out. You have 1/2 m naught v squared. The third term, the c squared cancels a c to the 4th, well, not entirely, but you get a term that looks like this, minus 3/8 m naught v to the 4th over c squared, plus, and so on and so forth, an infinite number of terms. Now, here's what I want to point out, is that the energy of an object can be understood as a rest energy, which is m naught c squared, plus a kinetic energy, or an energy associated with motion, where here all of these terms are understood as the kinetic energy. And here's what I want to highlight especially. Notice that when the velocity of an object is small, you have a small number to the 4th power, to the 6th power, and so on. These terms become very, very small, and it's common to simply truncate this series, or stop it right there, and you'll notice that the kinetic energy is just 1/2 m naught v squared for very small velocities, which is precisely our classical expression for the kinetic energy. In other words, in Einstein's theory of relativity, one arrives at the classical expression of the kinetic energy of an object, but there are corrections to that are there that are just small terms that one typically doesn't have to think about or worry about. Okay, so this would be the configurational or the rest energy, and this right here would be the kinetic energy. But again, the kinetic energy has a slightly different form. It's an infinite series in the theory of relativity, whereas in the classical theory, it is simply a single term, 1/2 m naught times v squared. Okay, let me say one other thing. What is the connection between energy and momentum? Well, if we were to put together our formulas for the momentum and the kinetic energy, one could write that the total energy of an object is the kinetic energy, and I'm going to plug in p over m for v right here. You'll get p squared over 2m naught, this is the kinetic energy, plus this potential energy. Okay, so this right here is once again the kinetic energy, the energy associated with motion, and this would be the potential energy, or the energy associated with rest or configuration. That's the connection between energy and momentum according to the classical theory. What about according to the relativistic theory? Well, the energy, and I'm just going to tell you what this is. I'm not going to derive this. I'll tell you what it is, and maybe in the next lecture, if I have time, I'll come back and explain where this comes from. It looks like this. E squared is momentum times the speed of light squared plus the rest mass times c squared squared. So this is the energy of an object in terms of its momentum and its rest mass according to the theory of relativity, whereas this would be the energy of an object according to the classical theory, the Newtonian versus the Einsteinian approaches to mechanics. This formula looks a little bit complicated, but there is a geometrical explanation or way to remember it. So let me quickly draw out that geometrical explanation. Notice it looks like a little bit like the Pythagorean theorem. So let's draw a triangle like this. And these two terms can be understood as the sides, and this can be understood as the hypotenuse. Okay? So the length of this side right here is, let's take this one right here, m naught c squared. Okay, so that would be the length of that side. That would be a measure of the rest energy of the object. What about this side? That would be PC right here. So that would be PC. And then this side right here would represent the total energy of this object, because E squared equals m naught c squared squared plus PC squared. So this obeys a Pythagorean triple relationship. And it might be helpful to think about it this way. If I were to draw an arc, if I were to take this base and I were to rotate it up like this and project it onto this axis like there, then the length from here, this would be m naught c squared. That would be the rest energy once again. So that much of the total energy is rest energy, and the leftover part, this right here, one could understand to be the kinetic energy. So the total energy consists of a rest energy plus a kinetic energy. And this kinetic energy is this infinite series right here. Okay? So there you go. There are some of the important formulas from relativistic mechanics, and I think I will, in my next lecture, which will probably be my final lecture, I will talk about how one arrives at this formula right here.